Okay guys, in this video I'm going to talk a little bit about crystalline lattice structures. And so really my goal here is just to give you a bit of flavor for the subject. It's not something that you need to worry about in any great detail. There are a lot of details in this section, but you don't need to worry about committing these types of things to memory. I mostly just wanted to show you some of the pictures. So the term crystal lattice, in chemistry at least, it refers to a typically symmetric three-dimensional arrangement of either atoms, molecules, or ions that repeats itself in all directions. So, and the smallest unit of the crystalline substance is called the unit cell. And so here's a simple cubic unit cell. And so you would imagine if you were to build a crystal, you would repeat that cubic unit cell in all three directions. Okay. The term lattice point refers to a point within the unit cell, so some relative positions within this unit cell. And then the crystal lattice refers to the geometric arrangement of the lattice points themselves. And so let's look at some. Well, here's some classifications. Okay, so there are 7 basic types of crystalline systems. You don't need to memorize these by any means. They are cubic, tetragonal, orthorhombic, monoclinic, triclinic, hexagonal, and rhombohedral. We'll look at some pictures of them in a minute. These different crystalline systems, they can be characterized as a parallelepiped that consists of 3 distances, which are labeled A, B, and C, and then there's 3 angles, alpha, beta, and gamma. And then depending on how you arrange the crystal lattice within the unit cell, you can come up with these with these different ways of doing that. So there's something called primitive centered, where you have all of the lattice points are at the corners of the unit cell. There's also body centered, where you have lattice points at the corners and one in the middle of the cell. Face centered, where you have atoms in the corners of the lattice of the unit cell, but then also points along the face of each side of the unit cell. And then there's also base-centered, crystalline lattices as well. All told, by combining these 7 basic crystalline types with these 6 different ways you can arrange the crystal lattice within the cell, you can come up with a total of 14 unique crystalline lattices. These are called the Bravais lattices, and they're illustrated here. So here we see the easiest ones to understand are the cubic unit cells. Here's a simple cubic system, okay, where you have atoms at each corner. Here's an example of a face-centered cubic structure where you've got atoms at the corners and then you've got atoms at each face. And here's the body-centered cubic where you've got atoms at the corners and then there's one in the middle. If it's not a perfect cube, if it's more like a rectangle, then you'll have the tetragonal structures. If the angles or if the distances, if all 3 distances are different, then you'll have what's called the orthorhombic structure. If one of the angles is not 90 degrees, then you have these monoclinic structures. If none of them are 90 degrees, then you'll wind up with this triclinic structure. A special case where 2 of them are 90 and one of the angles is 120, gives us the hexagonal structure. There's the special case of the rhombohedral structure. And so these are the different types of crystalline structures that you can have. Here's an illustration of the lengths, the A, B, and C length, and then the different angles between these axes, if you will. We'll focus basically exclusively on the cubic unit cells from here on out because they're easier to think about and visualize. So here we've got the three Here's the simple cubic, the body-centered cubic, and then the face-centered cubic. Note that the face-centered cubic in the textbook is also called, and in the literature, is also called the cubic closest packed, or CCP. It can be a little bit confusing because they're throwing out these acronyms, and then but FCC is identical to the CCP acronym. Just looking at the simple cubic structure, okay, think about the question that we're trying to ask ourselves is how many atoms are within the cubic structure, and note that only a part of the atoms at the corners are in the actual unit cell, and so you have to count up what fraction of each atom is at the corner and still within the unit cell. It turns out that for each corner you've got 1/8 of an atom within the unit cell. There's a total of 8 corners, so within the simple cubic structure there's really only 1 atom within the unit cell. Another factor that's often used to characterize different crystalline structures, this is the so-called coordination number, where one would count the number of nearest neighbors. And so here is a simple cubic structure, right? We have atoms just at the corners, and then let's count the number of neighbors around this center atom. And so there's 1 above, 1 below, 1 over here, 1 there, 1 back behind, and 1 forward. So the coordination number here for the simple cubic structure is 6. Okay, so these are quantities that one likes to know about for a different type of for the different types of crystalline structures. How many atoms are within the crystal structure, and then what's the coordination number for that particular crystal structure. Here we're looking at the body-centered cubic. Okay, so you've got 4 atoms at the corners and 1 in the middle. So the body-centered cubic is going to have a total of 2 atoms within its unit cell. For the face-centered cubic, it's a little bit different, right? You've got the 4 atoms at the corner, so each corner contributes 1/8 of an atom. But then the atoms that are at the faces, they each contribute a half atom, right? So you've got 1 for the corners, 1, 2, 3. So there would be 1 for the corners, 2, 3, total of 4 atoms within the unit cell. How many atoms are there in a face-centered cubic unit cell of an atomic crystal having 1 atom at each lattice point? So again, going back to the face-centered cubic, that's this one. As we said, there are 4 atoms in the unit cell. And then here in the follow-up question, they want us to think about a 2-dimensional square lattice with each atom at the lattice point. So that would be a 2-dimensional lattice would look like this. You can ask yourself, how many atoms does each corner contribute? Well, you've got 1 atom here, and that would be 1/4. 1/4 for each corner. You've got 4 corners, so 1 atom in the 2-dimensional square lattice. Here in these problems, we're asked to do some calculations. So we're considering a simple cubic crystalline structure for polonium. They tell us that the length of the unit cell is 336 picometers, and they want us to determine the radius of the polonium atom and then calculate the density of that substance. Well, here's a picture of the simple crystalline structure, and we know the edge length. And if you look at the picture, we can think of the edge length as being a full diameter of polonium. And so this edge length, the diameter is 2 times the radius of the atom. That's equal to 336 picometers. And so what would be the radius of the polonium? We take 336 divided by 2. We get a radius of 168 picometers. For part B, the edge length of the unit cell for nickel is 0.3524 nanometers. Oh, we need to do the density of polonium. I'm sorry, we'll go ahead and do the density now. So the density, right, that's mass divided by volume. Okay, it's a simple cubic structure, and so we know that there's one atom within the unit cell. And so we need to take the molar mass of polonium, which is 209. That's grams per mole. And then what will we do? We're going to divide by Avogadro's number, right? That's going to give us the grams per atom. And then what we'll do is we need to divide by the volume of the crystalline unit cell. Okay, the edge length is 336 picometers. So we'll take 336 times 10 to the minus 12 meters. And then we'll cube that. And that's going to give us the density in grams per cubic meter. So for the numerator, I'm getting 3.47 times 10 to the minus 22. Then we divide by 336 to the negative times 10 to the negative 12. We want to cube that. And I'm getting 9.15 times 10 to the 6. That's grams per cubic meter. It's not surprising it's so large since a cubic meter is so big. I should have really used a different volume unit. Let's do grams per cubic centimeter. That might make more sense. And so we'll say that there are 10 to the 2, well, there are 10 to the minus 2 meters per centimeter, and we want to cube that. Okay, so that's going to give us 10 to the minus 6. So 9.15 grams per cubic centimeter. So that's the number I'm getting from this calculation. The calculations for the nickel are similar, and so I'll leave those as an exercise for you guys to try. And we'll just look at a couple more pictures, really. So here we're talking about not atomic solids like we were before, but more on metallic solids. And so those usually form this face-centered cubic structure, or a hexagonal, which is a different crystal close-packed structure. And so here's just some pictures showing you the hexagonal close-packed structure and the cubic close-packed structure, which is the synonym for the FCC. And they look somewhat similar, but they're actually a little bit different. In the cubic close-packed, or the FCC, there are actually 3 distinct layers, and then they start to repeat after that. Whereas in the hexagonal close-packed, there's actually 2 layers. And it really just depends upon how you stack the molecules on top of one another, or the metal atoms, so to speak. And down below are the different stats for them. So the coordination number for the simple cubic structure that we looked at here in this example is 6. And then you estimate like how much of the unit cell volume is filled with an atom. And so for the simple cubic structure, it's about 52% filled. If you look at the body-centered cubic structure, you find that the coordination number is 8, and it's 68% filled. The closest packed structure, or the FCC, the coordination number is higher. It's 12 and it's 74% filled. And just like that, the hexagonal closest packed is also quite efficient. So there's a coordination number of 12. And the unit cell is 74% filled. These are the types of details that you can think about when you're talking about unit cells. These aren't parameters you need to memorize by any means at all. So don't worry about the details here. I just wanted to show you some of the pictures and the kinds of things that people talk about when they're talking about crystalline structures. Oh, here's another example from this one involves calcium metal. So calcium crystallizes in a face-centered cubic structure. The edge length is 558.8 picometers. What is the atomic radius of calcium in this structure? And then calculate the density. So it's the same kind of thing that we did for the simple cubic structure. It's just that the geometry of the crystal structure is a little bit different, and so it changes slightly how you do the calculation. And so what they're pointing out in this diagram is that the edge length is A, and then here we've got to do a little bit of, basic geometry where they're pointing out that the distance along the diagonal here, I don't know if I'm going to be able to draw it very well, probably not at all. The distance along the diagonal is, that distance is equal to 4 times the radius. Okay, so you use the Pythagorean theorem here, right? You'd say that the two lengths squared added together would be the hypotenuse squared. So if the hypotenuse is 4r, you square it, it would equal 2a squared. Okay, and now that you know you've measured a, you can find r. So you would take the square root, 4r would be equal to the square root of 2 times a. R would be the square root of 2 over 4 times a. And so you would plug in the value of 558.8 picometers, take it times the square root of 2, divide by 4, and you get a radius of 198 picometers. And then the calculation for the density would be the same, except for that you have to take into account that there are, what did we say? There's 1 for the corners, 2, 3, there are 4 calcium atoms. So when you go to calculate the density, you would need to take 4 times 40.08 grams per mole, divide by Avogadro's number, and then you divide by this 558.8 times 10 to the minus 12 meters, and you cube that, and so then that would give you the density of the calcium. You have to take into account that there are, in this case, more than 1 atom within the unit cell. There's 4, not just 1. I'll go ahead and run the numbers since we're almost there. 4 times 40.08 divided by Avogadro's number divided by 558.3 times 10 to the minus 12, and we want to be sure to cube that number. Okay, and so it's going to give us, I'm getting 1.53. That would be grams per cubic centimeter. So let's see. I think this is actually kind of a neat problem. So X-ray diffraction of crystals can be used to determine Avogadro's number. You'll notice that in these last problems of the density, we needed to use Avogadro's number to calculate the density. Well, if you measure the density and then you measure unit cell lengths using X-ray crystallography, then you can use that as a way of estimating Avogadro's number. So here we're talking about silver. It says that it's a face-centered cubic lattice. So that means that there are 4 atoms per unit cell. And then the length of the unit cell is determined. It's 408.6 picometers. The density is 10.50 grams per cubic centimeter. Use this to, it says, calculate the mass of a silver atom, and then use, using the known value of the atomic mass, calculate Avogadro's number. So let's just do the second calculation, where we'll calculate Avogadro's number using the known molar mass. So it's really just the reverse of the calculation that we did before. You know, the density is going to be equal to 4 times the molar mass divided by Avogadro's number, and then you would take the distance and you'd cube it. So rearranging this, we would say Avogadro's number is going to be 4 times the molar mass divided by the density times a cubed, and then the trick is getting the units right. So for the molar mass, we've got this 107.87 grams per mole. For the density, we've got 10.50 grams per cubic centimeter. And then for the we'll go ahead and leave that in grams per cubic centimeter, and then we'll do our work for the unit conversions. We'll do that on the distance here. So we've got 408.6 times 10 to the minus 12 meters. We want to, and that's cubed. We want to convert that to cubic centimeters. So we're going to say that for 1 meter there are 10 to the 2 centimeters, and then we need to cube that. So let's see what we get here for Avogadro's number. So I got 6.0199 times 10 to the 23, which I think you'll agree is pretty close. So indeed, we've done the calculation right. We got the number. We're in the right ballpark, that's for sure. Let's see, in this problem, it's just another rearrangement of these geometric ideas involving the face-centered cubic structure. So I'm going to go ahead and, if you're interested in this kind of thing, by all means, have fun doing the calculations. Again, these aren't super critical problems. I really just wanted to show them as illustrations. And so we'll go ahead and move on to the next set of pictures here. We'll start talking about ionic solids, and really the only thing that I wanted you to take away from what follows is that ionic solids can be quite complicated. So the crystal structures are generally much more complex than they are for simple atomic solids, just because you have different types of ions that have different sizes. On this slide here, as it says in the middle, if you have large ions, they will typically form a close packed structure, and then small cations are going to fill in the holes in the close packed structure. And it just depends on the nature of the cations, what kind of holes they fill. So there's tetrahedral holes, there's octahedral holes. It really just depends on the cation and the anion and what sizes you get. So here is an example of showing you a close packed structure. So these spheres, these represent the anions, and they would all be the same. They're just colored differently to show you the different layers. Okay? And then what they're pointing out here, these are the different types of holes that can be filled with cations. So depending on the size of the cation relative to the anion, you're going to get different crystalline structures out of it. And so they're trying to illustrate the three different structures that you'll get. I find these diagrams a little hard to look at, but anyway, there they are. There's different so there's different themes that are similar, so a lot of different compounds have similar structures, and so there's the cesium chloride structure that you're looking at here, where you've got the anions are on the corners of the crystalline structure, and then the cation is in the center. Okay. So it's a simple cubic structure of anions with the cation occupying the middle. Here's a sodium chloride structure. Okay, it's got a face-centered simple cubic structure where the cations fill in the octahedral holes. And so, what you wind up ultimately with is the cations are surrounded by the anions, and the anions are surrounded by the cations. But then, there's a whole assortment of details that go into the geometry of the unit cell as well, where the cations are, where the anions are. Another motif is this zinc blende structure, zinc sulfide structure. You have a face-centered cubic cell where you've got the sulfide ions are at the lattice points, and then the zinc ions they're occupying some of the tetrahedral holes of the structure. In any case, this is the yellow. The yellow shows the zinc ions where you've got the sulfur, where you've got sulfur at the corners and then at the faces, and then the zinc ions are kind of scattered in particular holes in that structure. I don't think we need to do any more of these crystal structure calculations, but it's the same type of game here. Now you've got different types of ions present. So you've got both cations and anions present in the crystal structure. You measure the distance, you count the number of ions and the number of radii along a particular distance, and so you can use the measured unit cell to, for example, predict the ionic radius for a chloride ion. Okay, so it's a combination of geometry and experimental data that you use to estimate ionic radii, for example. Here's just some additional vocabulary for this type of for talking about crystal structures. So, real crystals they don't extend forever, and they aren't perfect with an atom at each lattice position as they're supposed to be. There can be impurities. There can be vacancies. There can be impurities between atoms. So there's all kinds of defects that you can have in a real crystal, and in fact, some of the defects are in particular in electronic devices, which are based on often based on solid structures. Often the defects are put in purposefully to serve a particular function. So if you they call it doping. If you add certain types of elements to a crystalline structure, it gives that substance desirable properties in terms of making the electronic device function. The last couple of slides here, these are just meant to identify the technique called Xray crystallography. It is the technique that's used to measure the geometries of unit cells. It's based on the idea of diffraction. We talked about diffraction of light a while back in chapter 6, I believe. Whenever you have light pass through an opening or an aperture that's comparable to its wavelength, you'll find that the light bends around the structure. That's what diffraction is. And you'll get interference between the different, between the within the light. You'll see bands of constructive and destructive interference, and it turns out that the distance between atoms within a crystal are comparable to the wavelength of X-rays. And so the technique of X-ray diffraction or X-ray crystallography, one uses beams of X-rays, shines them on a crystal, and then one measures or detects the diffraction pattern coming from the crystal. And so it would look something like this, where it's a pattern of light and dark patches. And it turns out that you can mathematically relate the crystal pattern to the crystal, you can relate the diffraction pattern to the crystal structure of what it is you're studying. And so this, for example, is how we know what the structure of crystalline unit cells are through X-ray diffraction. Oh, and here's just some more pictures illustrating the things that I've been talking about: constructive and destructive interference, and then the idea of shooting the X-rays at a crystalline material, and then you measure the diffracted pattern, and you see these bright spots and dark spots, and then the particular pattern that you measure corresponds directly. Well, it's related to the structure, the crystalline structure of the material that you're shooting with the X-rays. So with that, that's the end of it, and so I'm going to go ahead and stop this video right here.